Hi, welcome back to Engineering Mechanics. Today we are going to talk about how to do dynamics of motion in a non-circular but periodic path, repeating paths. Why do we care about it? Because a very important aspect of mechanisms are things where motion has to be repeated in a certain way, and they're usually done with the means of cams. So that's one of the things that we are going to talk about. So I'm going to talk to you a little bit about what is meant by a cam and how it works. And that's an important idea. So let's move on. Okay, before you start it, what you should know before you do this thing is how to find position, velocity and acceleration vectors in polar coordinates. What I would like you to do is, if you don't have the expressions handy, go pause this video, go get a piece of paper, write down the position, velocity, acceleration vectors in polar coordinates because we will use it. Also, you should know the meaning of tangent and normal vectors for a given path. Tangent is along the path, normal is in the plane of motion pointing inwards. So those two things are very important. And before you start, you should know what is the meaning of a cam and how it moves. If you don't know what it is, pause and go to this website. It has a beautiful explanation along with animations of cams. This is well worth it. It will just take you 5 minutes, but it is well worth it. Okay. So, did you pause? Did you do all these things? Okay, now let's proceed. What are we trying to do? We're trying to learn how to describe the path of a follower in a cam, how to do dynamics of a cam, how to use polar coordinates, but unfortunately forces will be in tangent normal directions. So you have to make some geometrical connections between these two, and I'll show you how to do it. And putting everything together to find the output. In this particular case, maybe you're interested in how much force it takes. Particularly, you may be interested in how much friction and normal forces, because that's what causes the cams to wear out. Okay, so that's something that we are very much interested in. Okay, so let's see what's a cam. A cam is a circle of varying radius. So a cam path is a circle of varying radius. So if you imagine an ordinary circle, looks like that, and you can see that r is constant. But a circle of varying radius, so if this is x and y, so if I have something like this, can you see that r now depends upon theta, and this is some function of theta. So just like we have y equal to f of x represents a curve in Cartesian coordinates, r equal to f of theta represents a curve in polar coordinates. In this case, theta is like x, r is like y. Okay, so I've shown you, if you put r equal to sine 3 theta, you will get a curve that looks like a 3-leaf clover. If you put r equal to 5 3 theta, sine 5 theta, you can get a 5-leaf clover. You can get all kinds of shapes. Can you see all these wiggly shapes? You can get a variety of shapes and designs if you plot things in polar coordinates. It's much more fun than plotting things in Cartesian. So if you do if you use the command polar in MATLAB, theta and r, and you know how to draw functions, right? You have to create vectors which have r as a function of theta, and then you can use the command polar and it will plot this in polar coordinates. You can try it out if you like. Okay, so basically r equal to f of theta is how curves are defined in polar coordinates. My task to you is try and draw a 5-leaf clover by using r equal to sine 5 theta. Go play around with it and see if you can actually plot this. If you are more familiar with Mathematica, just go to Google and Google polar plots, and then you will find both in Mathematica, Maple, MATLAB, all of these things, and then you can plot these things. Okay, so but what we are interested in is velocity and acceleration. So let's say I have a cam like this. So here's the center, and let's say this is the x direction, y direction. So what it is that we are interested in how this particle moves along this path, right? And the way in which we are given is theta of t, that's the input, and I'm given r equal to f of theta. This is what I'm given. So that's the shape that will define this curve, and the input angle is theta, and then the position vector is er is like that, e theta will be something like that. By the way, e theta will not be along this is a very important thing. So for example, let's look at a nice situation. Most of the time it looks almost like that, but let's pick something here. Let's pick this point. You can see that ER is like that and E theta will be like this, right? And if you remember your tangent normal directions, you will see that the tangent direction is actually something like this and the normal direction is something like that. So I want you to understand it will not necessarily coincide. So now we want to be able to find the velocity vector and so on. So let's look at this thing. So remember, I'll compare and contrast Cartesian. So I'll draw position, velocity, acceleration. In Cartesian, position looks like xi plus y of xj. Correct? In polar, it looks like r of theta j. Sorry, er. Notice it does not have two things, it has only one because er is very convenient. Okay, so that's my position vector. Velocity vector is x dot I plus dy dx x dot j. Can you see that? Because that's chain rule. Similarly, if I calculate velocity here, you remember it was r dot er plus r theta dot e theta, right? So if I write this down, r dot will turn out to be dr d theta theta dot er plus r theta double dot e theta. Sorry, r theta dot e theta. Right? So you can see how, just like we use chain rule here, we are going to use chain rule there. Then acceleration is very messy. Acceleration vector, it's x double dot I plus I have to use both chain rule and product rule. So I'll get d squared y dx squared x dot squared, because there's a x dot already there, I'll get another x dot squared plus dy dx x double dot j. This is in Cartesian coordinates. It's kind of messy, but here you will get a much bigger mess because there are lots of chain rule and product rules. So we are going to do that. In polar coordinates, the acceleration vector looked like r double dot minus r theta dot squared er plus 2r dot theta dot plus r theta double dot e theta. Right? So now if you look at this, I know that r dot is dr d theta e theta dot. Can you see that? That's where we got from here. Right? So r double dot will be d squared r d theta squared theta dot squared, because there's already a theta dot here, and then I get one more plus dr d theta theta double dot. So notice I got to differentiate everything inside. That's what I said about chain rule and product rule combined. And then I have to take all of this and substitute here, and I'll get a big mess. So I want you to understand that computing velocities and accelerations are messy in for CAMs. But there is another problem which we are going to talk about, and that's why we need to be good at doing chain rule and product rule again and again and again. Okay. So what we are going to do is we will set up a nice table so that we can do this in an efficient way. Okay. Now let's come back to this CAM. So I got a strange looking cam like this, let's say. Okay, and so my x direction is like that, y is like that. Let's say I pick a point here. I want you to understand now something rather painful. If I look at my forces, unfortunately, if I look at a point here, what happens is my friction force is going to be like this, and my normal force is going to be like that. Unfortunately, my ER and E theta directions are going to be like this. So I have problems, which is that I have to be able to find. So if here is the curve, so let's draw this and you'll see where the issue is. Here is the curve. Let's say here's the point I'm interested in. And my conventional ER direction is like that. And let's say my E theta direction, let's draw this right. Let's say my ER direction is like that, because that's the origin, and my E theta direction is like this. Unfortunately, my tangent and normal directions are going to be this way. Tangent and normal are going to be like that, and forces are along this. So this gives us a problem. So what it is that in many cases I want to find the value of psi. Now how do we do that? The trick is the following. The velocity vector is tangent to path. So velocity is like this, right? So psi is the angle made by velocity vector with positive theta E theta axis. And that's pretty easy because our velocity vector looked like r dot ER plus r theta dot E theta, which turns out to be dr d theta theta dot ER plus r theta dot E theta. So tan psi equal to opposite over adjacent, which is r dot divided by r theta dot, which turns out to be dr d theta theta dot divided by r theta dot. I can cancel it out, and I will get a very nice expression which says that my tan psi is dr d theta over r. Or I can just use Vr over V theta, just like I use tangent equal to Vy over Vx. Okay, so that will give me this counterclockwise direction, that is from E theta towards ER. So once you have this, then we are in very good shape, because we can now continue and convert and figure out all the other informations. Okay, so sometimes we will use this, sometimes we will use that, whichever is convenient, dr d theta over r or Vr over V theta, whichever. Okay, so how do we use this? Let's look at an example problem. So here it is. I got something that's going along this kind of a spiral, and I'm applying a force on it, and the force is such that it is going at a constant speed, angular speed. Theta dot is 2 radians per second, and I'm interested in the applied tangential force F, and the normal force N acting on this. Okay, and it maintains a constant angular motion theta dot equal to 2 radians per second, and I want it at theta equal to 90 degrees. Where is that? So I want you to understand, I want it here. So first thing to do, that's the first thing to do. So I'm going to go up here and I'm going to say ER is like this, theta is increasing this way, so E theta is like that. Can you see that? So the next thing we are going to do is we are going to do basic kinematical calculations. So this is where we will need all our wits about us, because we got to do this right. So the way I'm going to do it, I'm going to write it as position, velocity, acceleration. What's the input information given? I want theta equal to pi over 2. Please do this in radians, otherwise you'll run into problem. That's the point I want, position. I want it here. And I'm given theta dot equal to 2 radians per second. Right? Theta double dot equal to 0. All of this is given. So because of this, I know R equal to E to the theta. So at this position, R will be 4.8105. So substitute meters. So position vector will be 4.81 ER meters. That's position vector. Okay. So this position, so this length is 4.81. Remember, ER is like, E theta is like that, ER is like that. Okay, so now we know that R dot will be dr d theta, theta dot from here, and then I'm going to substitute and I will get, that is e to the theta, because dr d theta is e to the theta, theta dot, which turns out to be 9.62 meters. So velocity will be r dot er plus r theta dot e theta, which turns out to be 9.621 er plus, we know r is 4.81, theta dot is 2, and if you do that, I'll get again 9.621 e theta. So I know the velocity now. So velocity vector is along the tangent, velocity vector. So this angle psi is Vr over V theta, tan psi, which turns out to be 1. So psi is pi over 4, which is 45 degrees. Very nice. So I know this angle is 45 degrees. That will make us huge advantage already. Acceleration, for acceleration I want to be able to compute r double dot, which is d dt of r dot. If you do that, you will find that I will get e theta theta dot squared plus e theta theta double dot. Do the differentiation, differentiate this twice, differentiate this once more, and you'll get this. At the instant that we are looking at, now I am going to substitute these values and I'll get r double dot turns out to be 19.92. So my acceleration vector A is some messy thing, r double dot minus r theta dot squared er plus 2r dot theta dot plus r theta double dot e theta. So what happens is I will get acceleration in the r direction turns out to be r double dot minus r theta dot squared, that's 0. Acceleration Substitute and see. That's what I'm saying. It's not 0 because r double dot is 0. Just substitute. R double dot is 19.92. If you compute r theta dot squared, it also turns out to be 19.92. So it happens to be 0. A theta is 2 times r dot theta dot plus r theta double dot. This term is 0. So this turns out to be 38.48. So there's AR and there's A theta. This table is what you have to create, and this is all I want you to remember: chain rule plus product rule. So please remember, this takes some effort. So pay attention, look at how I derived. My best explanation, the best way for you to do is you sit and do it. What I would like you to do is pause it, do this entire table by yourself, and then you will see where the terms come from and whether I'm correct or not. Okay, so please do that. That's very important. Okay, so now we got all the information that we want. Now we do the next thing. So we are going to draw the free body diagram for this. Remember, the path was something like this. Right? So at the point was ER was like that, E theta was like that, and it says smooth collar, so no friction. So the forces are normal force acting like this, that's the tangent direction, and this angle was 45 degrees. Oops. Psi equal to 45 degrees. So this angle happens to be, this is the direction of gravity, mg, and then there is a force F acting here. Right? This angle is 45 degrees, that angle is 45 degrees. Right? So this is the sum of all the forces, must be equal to the acceleration vector. Same way I'm going to draw. That's the curve, that's the point of interest. ER is like that, E theta is like that, and we found that AR equal to 0, and we found that A theta equals 38.48 meters per second squared, going that way. And then so this mass times mass times that. Okay, so now we can write down the retail equations. So if I sum all the forces, ER direction, FR mass times AR gives me n cos 45 degrees plus t cos 45 degrees minus 2 times 9.81 equal to 0. Summation of all forces this way, F theta, E theta is the direction in which I am summing, equal to mass times A theta, which gives me n sine 45 degrees, minus plus t sine 45 degrees must be equal to 2 times 38.48. So solve for n and t. N will turn out to be minus 40.54 newtons. That means it's not pushing out, it means it was actually this way, right? And I just got the direction, the arrow wrong, but that doesn't matter because my force will show out, and the force, not T, it's F. So F turns out to be 68.3 newtons. See how this process goes, right? So let's quickly cycle through the process. We start out, we first identify the location of interest and draw ER and E theta. Then we create a kinematic calculation table that will help us. Position, velocity, acceleration, write down the given information here. And for cams, it will always be something about theta, theta dot, and theta double dot. And then this is my equation for the curve r equal to e to the theta. Find the radius, do r dot, and then you will find velocity is r dot er plus r theta dot e theta. If you compute that, then you can find tan psi. This will be very useful for you. And then you find the acceleration. Again, you have to do the acceleration formulae and substitute terms. And everything is chain rule and product rule. So pay attention to this particular slide, okay? Because everything happens here. Then you can create a force table and you can draw the forces. Notice that the gravity is always down, so it doesn't really matter which way the ER and E theta are. Gravity happens to be always down. And then you have to find normal and friction forces. In this particular case, even my driving force is along the shaft. So I have to do all these angles. So once I calculate this angle psi, I can compute this and this. And then we write down the equations of motion. Equations of equilibrium and solve it. Okay. Thank you very much.